Welcome everyone. The quantum computers are coming. My name is ALASDAIR COLLINSON. I'm a software developer at Zenarcor Technologies and blah, blah, blah. You didn't come here to hear about me, did you? There's one thing about me that you should know, though. I'm a nerd. And though many other nerds are, I am not a physicist. Nevertheless, I'm here today to speak about quantum computers. And I mean, how does that work? Well, we're getting to a point where you don't have to be a genius physicist to get into quantum computing nowadays. And that's a good thing, because I mean, I'm looking at you here. You know, one of the last sessions for the day. It's been a lot of material to take in, I'm sure. And you're sitting here in a session about quantum computers. I think that you two are nerds. So, as I said, being a nerd is enough to get started with quantum computing. Let's do it. And, I mean, quantum computers, 2 words. Let's start with the easier one, computers. What's a computer? Well, I mean, that's a computer. A bit older, probably a bit bulkier than what you're used to. This is the Zuse Z3, well, a replica of the Zuse Z3. And when people argue about what the first computer was, the first ever computer, this is certainly a contender. It's a bit difficult to define, but this is one of the computers that's in the game here. It certainly is the first computer that was electronic, programmable, and binary. Those 3 factors were first in this machine. And binary is the most important of those, at least for this talk, because chances are that every single computer you've ever interacted with, either directly or indirectly, was binary in nature. And binary computers can do loads of things. But, I mean, what does binary mean? So, I mean, we often think of zeros and ones, but actually that's not quite correct, is it? I mean, as far as we're concerned, you could have a green circle and a red triangle. As long as you have 2 distinct states, you can work binary operations on it. Now, computers nowadays use transistors. Well, not so much those transistors. They look a bit more like this, microtransistors. But the principle is very simple. They have 2 inputs, and if the total, I think it's the total voltage is high enough, it will give an output. Otherwise, it won't. Well, it always gives an output, just higher and lower voltages. So those are 2 distinct states that we can work with. And as I said, this is really powerful. The whole point of computing, the reason all of us are here today is because you can do a lot of stuff with binary computing. But it does have its limits. And now, to some of the nerds in the room, this following image might be a bit shocking. Nature. I know many of you don't like to go out there, but nature is actually a really good example of a source of non-binary problems. So let's zoom in a bit in here. And so that part there that you see, that's certainly forest. And this part there certainly isn't forest, right? What about that part? I mean, there certainly are trees there, but most of it is grassland. So we have to make a decision. We have to draw an arbitrary line saying, for example, if you have so-and-so many trees per whatever measurement of area you want to use, that's a forest, otherwise it isn't. Or some other decision. But we have to make a decision. We have to split it into 2 options, into binary options. And that means we're losing information. So, quantum may be able to help us there. Next part, quantum. So quantum, of course, is related to quantum physics, quantum mechanics, and that was initially thought up by 2 guys, Niels Bohr and Carl Werner Heisenberg. And they were working together in Copenhagen in the 1920s and came up both with the basics for quantum mechanics and with the so-called quantum, the Copenhagen interpretation of quantum mechanics. And I'm going to get into that interpretation. So, I mean, the explanation I'm going to give you is highly simplified. If there are any physicists in the room, please don't hit me for this. Copenhagen interpretation by example. So let's take an atom. Actually, we don't need the whole atom. We just need to look at the nucleus of this atom. And let's say this atom is radioactive. What that means is that at some point, we'll measure that part of the nucleus leaves the rest. This is radioactive decay, and that little particle here, in this case an alpha particle, though it doesn't have to be, is the radiation part. So if we have one of these atoms, and we wait for a certain amount of time, there are two states that we could measure. Either, well, nothing's happened, still the same nucleus, or it has decayed, right? According to the Copenhagen interpretation of quantum mechanics, however, we can have that. Both of those states exist simultaneously. They overlap. That is, they overlap until a measurement is made. I've displayed the measurement here as eyes. Please don't confuse this with the need for human consciousness or anything. Quantum mechanics works perfectly fine without the need for humans, but that's the easiest way to display what I mean. So this whole thing is weird. One thing in two states at the same time is weird, and we're not the first people to think it's weird. A famous example of someone who thought this was weird is Schrödinger. So Schrödinger came up with a rather famous thought experiment to demonstrate why he thought the Copenhagen interpretation of quantum mechanics was weird. And that's, of course, Schrödinger's cat. So let's go through that experiment just very quickly. We have, of course, a cat. This cat is in a box. In the box, we also have a few other things. One really important thing we have in the box is a radioactive isotope. Now, this is very similar to the radioactive atom we saw earlier. There's just more of them. And this isotope, this mass, radioactive mass, is chosen in such a way that if 1 hour passes, the chance that we measure any radiation from that isotope at all is 50%. So we have that in there. Also, we have a bottle of gaseous cyanide. Now, cyanide, as you probably know, is quite poisonous. You don't want to breathe that in. But I mean, as long as it's in the bottle, we're fine. And so is the cat. And then there's this thing. This weird contraption is a Geiger counter to which a hammer has been attached. And if that Geiger counter registers any radiation whatsoever from that radioactive isotope, this happens. Not pleasant. So we wait for an hour. And after that hour, there are two states that we would expect to find if we open the box or look into it. You know, there might be cyanide there, so better not look too closely. But there are two states. First, you know, nothing happened, and the cat's fine, or dead cat. But again, according to the Copenhagen interpretation, you can have both of them, and they overlap. I mean, how can anything be dead and alive at the same time? I don't think Schrödinger was thinking zombie cats here, but it's certainly very weird. And Schrödinger did believe that quantum physics made sense and that it was correct. He just thought that the interpretation that Bohr and Heisenberg had proposed was nonsense. So he came up with his own interpretation, which is the many worlds theory. So before I get into the many worlds theory, I have a small disclaimer. We will be using the many worlds theory as a model here. And models, as they go in science, can be wrong in many, many ways. That is, they can be wrong just as long as they're wrong in ways that we don't care about. Whether the many worlds interpretation is correct or not is still open to debate, and physicists love debating those two and a number of other models that may explain quantum mechanics. But for our purposes, the many worlds theory helps us think about how quantum mechanics works well enough for us to get into quantum computing. So, how does it work? First of all, you take the universe. And yes, I know this is a picture of a galaxy. I couldn't find a picture of the universe. But, well, let's just continue with this. So in this universe, among other things, of course, you have the cat. Now, one of these radioactive events happens where, according to Heisenberg and Bohr, the cat would overlap and be in two different states. Instead of getting our zombie cat, however, something happens that is really simple in theory, and that's the universe carbon copies itself, with one exception, and that's the event and the result of the event that happened there with the radioactive isotope. It's wonderful. Carbon copying the universe is a simple explanation. But so this can repeat itself, of course. If you have another event, you'll get 4 universes. There we go, 4 universes. And if another event happened, we have 8. So, you get the picture. It quickly multiplies. One thing you might notice about this picture, however, is that we have rather many dead cats. And this is actually not the fault of quantum physics. This is the fault of biology, because in our, well, in this case, multiverse, I guess, if you have a dead cat and add more poison, you don't get a live cat. Blame the biologists for that. Luckily for us, cats and quantum computers are different in that aspect. So finally, we've arrived at quantum computers. What do we have here? Well, this is a representation of a qubit. A qubit is to a quantum computer what a bit is to a binary computer. And this representation of the state of a qubit is called a Bloch sphere. So in this Bloch sphere, we'll have a vector. And this vector could point up, which means that if we were to measure this specific qubit, we would get the value 0, always. If we have a vector pointing down and measure it, we'll get the value 1, always. But, I mean, this is a sphere. It can do more than point up and down. It can also point, somewhere sideways. And this is actually a really interesting case, because if we were to measure this qubit, we would get, with this specific vector, 0 in most cases, because the vector is much closer to the 0, much closer to the top. But we would get some 1s in there. And we can do some really interesting things with these qubits. So in binary computers, we use binary gates, and everything is built up from there onwards. In quantum computers, we have quantum gates. So the first quantum gate I want to speak about today is the Hadamard gate. The Hadamard gate imagines that between the x and the z axis there's a further axis, an xz axis. And it will then spin our vector around that. So if we were to measure our qubit in this state, we would get 0 and 1 in 50% of the cases each. And this is what's called quantum superposition. That's what we mean when we say that something is overlapping in state. So this is basically the state that Schrödinger's cat was in when we said it was both alive and dead. Alternatively, it's dead in one universe and alive in another. Another gate, which is rather simpler, is the X gate, the Pauli X gate. So this just takes the x-axis, as the name suggests, and spins our vector around that. What we have here is basically a NOT operation around the x-axis. There are, by the way, Pauli gates called Y and Z as well, which just spin around the appropriate axes in the Bloch sphere. This is rather boring just by itself, but then comes the C-NOT, the conditional NOT gate. So this is the only 2-qubit gate I'll be speaking about today. There are others, but I'm not going to get into those. And so we have a source gate here, which is pointing towards 0. Then we apply the C-NOT, and, well, nothing happened. The condition part of the conditional NOT was that that is not 0, that source gate, that's 1. So if we have it at 1 and apply our C-NOT, then we'll get the spin we saw with the X gate previously. So far, not that exciting. This is basically if then else. What happens now? If we apply a C0 and the source gate is in superposition, something a bit like this happens. We suddenly have two arrows in that. Well, actually, it's more like this, at least at the point where we measure it. Both gates will either be in 0 position or in 1 position. They're linked. This is what we had with Schrödinger's cat and the radioactive isotope. This is what's called quantum entanglement. These two qubits will always have the same value, or if we applied an X gate to one of them previously, they'll always have opposite values. And as long as we don't measure, they'll both just remain in superposition. And normally there should be eyes up there. I don't know why PowerPoint is not showing those. Anyway, as long as we don't measure, they will both be in superposition. And these few gates already allow us to do a few things that are quite interesting. So I've talked about the Hadamard gate and the C0 gate, talked about one of the Pauli gates and mentioned how the two others work. I have not talked about the identity gate, simply because it's boring. It takes a gate and does nothing with it. I did not talk about phase gates either. Now, they're certainly not boring, but they're too complex to get into right now. And there are a bunch of other gates that you could imagine, and some people have imagined and integrated into quantum computing models. Now, everything I've talked about so far and everything I will be talking about in the rest of this presentation is the so-called quantum circuit model. You may have heard about a company called D-Wave, and they're producing commercial quantum computers and have been doing so for quite a while. Those are so-called quantum annealers. And not to get too much into what the difference is, but basically a quantum annealer can do a subset of what a quantum circuit model computer can do. And those can still be really, really powerful and really useful. But that's not what I'm going to be talking about today. I'm going to talk about the more powerful version, which, as you will see, is well, not really just coming, it's upon us. What do we need quantum computers for, or what can we use them for? There are a bunch of things. One topic that a lot of people agree will be the first where we see real results from quantum computers is quantum chemistry. So simulating quantum chemistry is a really hard task. If you have a computer which itself is quantum in nature, that does make stuff much, much easier. So we could see advantages from that in, say, the medical field or material research and so on and so forth. We're seeing first successes with quantum computers in the engineering field. Here, Lockheed Martin, NASA, and Volkswagen, they all, by the way, used quantum annealers from D-Wave. So that's results from something more limited than what I'm talking about, but still pretty amazing. Volkswagen used the quantum computer, for example, to enhance the capacity for batteries of their electrical cars. Quantum machine learning, AI stuff, that's had a bit of an upsurge in the last, I'd say, 2 or 3 years. There was a paper published a few months ago about an algorithm called quantum kitchen sinks, which is a quantum-supported machine learning algorithm which showed better results than comparable non-quantum machine learning algorithms. Weather prediction. Weather systems are really, really complex. And if I spoke about half a year ago at Vox Days Bucharest as well, and on the day of the conference, there was a snowstorm that nobody had seen coming. One of the speakers was diverted and couldn't give his talk. And weather predictions have gotten much, much better in the last, let's say, decade. But there's still room for improvement. And complex systems quite possibly can be modeled more efficiently with quantum computers. If you think weather is difficult to model, try humans. Financial fraud detection is a really, really big topic, and people are thinking about whether they can use quantum computers to model human behavior more accurately so as to detect when fraud is happening. And of course, there's the big example, encryption. If you've heard anything, actually that's one too far, if you've heard anything about quantum computers in media, it's that it's going to break encryption. That's because there's an algorithm called Shor's algorithm, and that's really, really good at factoring large numbers. Now, most encryption algorithms today are based on the fact that factoring large numbers is really difficult and expensive. When we get quantum computers powerful enough to do that, those algorithms will be, well, I wouldn't say useless, but more in danger. And of course, related to that, cryptocurrencies. So right now, we don't have quantum computers powerful enough to endanger your cryptocurrencies. So with Bitcoin, I wouldn't say you're safe. You're never safe with Bitcoin, but you're safer than you will be when quantum computers get powerful enough. And then there are fun things like, here's a project where someone used quantum computers to compose music. Sure, why not? Now, I've been talking about what other people are doing in quantum computing and a bit of the basics on how it works. But why am I giving this talk? Well, the field of quantum computing needs more people to join, especially people who have experience in practical software development. A lot of the people who are in the field currently are physicists by training, often working for universities, and they've been doing a great job, other research institutions, I should say. They've been doing a great job, but they work with what they know, and we come from a totally different perspective as software developers, so we can help take this field to where it becomes really useful to us. Now, that's why I would like you to start playing with this field. Why should you? I mean, there's certainly the point of job opportunities. A few months ago, there was a quantum job fair in Bristol, and that's fine, but I mean, realistically speaking, we're all going to find jobs. I mean, there are plenty of jobs on the market for software developers. Much more interesting, who saw Venkat's keynote earlier? Nobody? Okay, one person saw the keynote. Here's that keynote basically in a tweet. If you learn programming languages that are different to what you've known previously, that will expand your horizon. It will make you think, it will help you think in different ways and solve problems in different ways than you would otherwise. And quantum computing is really different. And Venkat says, learn languages that hurt you. Quantum computing will screw with your brain. But it's so rewarding when it works. Okay, let's say I've convinced you to start looking into quantum computing. How? I mean, you can hardly buy a quantum computer, set it up at your home or your office, and start playing with it. Luckily, you don't have to. I'm going to show you 3 ways that you can get into quantum computing today. And the first one is the IBM Quantum Experience. So the IBM Quantum Experience is basically quantum computers in the cloud. IBM has built actual quantum computers, and the quantum computer is in here, but that isn't the actual quantum computer. The actual quantum computer looks like this. Specifically is a 7-qubit quantum computer. That's contained in a huge cryostat, basically a freezer. And it's cooled down to temperatures of millikelvins above absolute zero, colder than it is in outer space. And I mean, you can set one of those up, and some universities certainly have done that, but for private use, my freezer has an electricity bill high enough, thank you very much. And they've made this available via the internet. So this is the entry page to the Quantum Experience, And if you register there and log in, you'll spend most of your time here. By the way, all of the links will be available at the end of the presentation, so you don't have to worry about that. You'll spend most of your time here, and at the top you get some information about the quantum computers that are currently available to you. In this case, one of them is active, one of them is in maintenance mode. That is often the case. It also gives you details on how cold exactly it is and a bit of the architecture of the specific chip, and so on and so forth. We don't have to care about that most of the time. More importantly, we have this part down here. Now, this is called the quantum score within the quantum composer, named so because it looks a bit like a musical score. But this is for building quantum algorithms. And at the side here, we have the gates I spoke of. The H there is the Hadamard gate, the X is the X gate, that circle with a plus in is the C naught, and there are a bunch of other gates I haven't talked about. We don't want to care about those. Now, let's build an algorithm in this. And since we've already seen it, we'll build the algorithm of Schrodinger's cat. So what do we need? We need the cat, obviously. We need something representing the isotope, something representing the poison, something representing that Geiger counter thing in the wrong order, but never mind. And those have to be sequentially linked. So let's put those into the quantum score. There we go. We have, as our isotope, a Hadamard gate. The Hadamard gate puts a qubit into superposition, and that's exactly the state we will have with our isotope. And that is linked via a C0 gate to the qubit representing the Geiger counter, is linked via a C0 to the cyanide, linked via a C0 to the cat. And looking into the box is represented through this pink gate here. That's called the measurement gate. Actually, let's not just measure that one qubit, let's measure all of the qubits we've operated on. And having written this, you can send this as a request to IBM. They will run it on their quantum computer, or in a simulator if you like, that's faster. But you get more realistic results on the real thing, of course, and you'll get something that looks, for example, like this. So I ran the experiment 1,000 times, and what do we have? So here at the, whoops, that's too fast. Here at the beginning, we have the results where nothing happened. At the bottom there, you'll see all zeros. So in about 30% of the cases, nothing happened, the isotope didn't decay, the cat's alive, all's well. In another approximately 30% of the cases, everything happened. The isotope decayed, blah, 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 cat's dead. But then we have this. And remember, I said 30% each approximately. That adds up to 60%, and there's 40% left somewhere. Yeah. Error. The quantum computers that IBM and others have built are very, very early prototypes. They work, but they are very error-prone. This is due to a number of facts, which I'm not going to get into. Fact is that quantum error correction is a really, really big topic that a lot of really smart people are working on, and these things are getting better. It'll just take some time. In the meantime, we have to just know things won't work out exactly like we would expect them to do in an ideal world. But then, I mean, the same is true for binary computers. We just have better error correction mechanisms in those. Now, you can use the web interface with the IBM Quantum Experience, or there's Kisskit. So Kisskit Terra is a Python library which allows you to do basically exactly what I showed you previously. You define your gates, which operate on various qubits, you run your algorithm, you get a result. And then there's Kisskit Aqua. Kisskit Aqua builds upon Kisskit Terra, and it adds pre-made algorithms for a bunch of fields. It has algorithms specifically for chemical questions, quantum chemistry applications. It has algorithms for optimization problems, for machine learning, and this is quite new actually, for financial applications. Now, For all of these, you do have to be domain experts in the relative field. I had a look and tried to work through one of the chemistry examples, and I quickly got lost because I just don't know chemistry at that level. But really importantly, you don't have to be an expert in quantum computing to use these. It helps, no doubt about it, but you can get started without knowing your way around a quantum computer using Kisskit Aqua. So that's a really, really useful tool that, as I said, you can start working with right now. The second tool I want to get into is the Microsoft Quantum Development Kit. Microsoft is also in the working in the area of quantum computing, and they decided, okay, Python's nice, but we want something that's specifically designed for quantum computers. So they created a new programming language called Q#. Let's have a look at some Q#. So this is a small algorithm written in Q#, exactly the same algorithm, in fact, as we saw previously. And yes, some of it is blurred out. I'll get to that later. So we start defining exactly what we did previously. The Hadamard gate on the qubit representing our isotope, a C0 to combine that with the Geiger counter, a C0 to combine that with the poison, and a C0 to combine that with the cat. And that's basically exactly what we had in our quantum experience experiment as well. What else do we have? So first of all, we have here a mutable field. By default, in Q#, fields, or values I should say, are immutable. In this case, we want one specifically to be mutable. That can be defined. Then we apply an M, a measurement gate, to the qubits. Specifically, in this case, to the Schrodinger's cat qubit. We aren't measuring the other ones here. And then we return our result, representing whether the cat survived or not. Then we have a bit of, well, boilerplate code, really. We define that we want to use 4 qubits for this. Okay, I mean, that's important information. And then we give the qubits names. I mean, naming values is really important, not just in classical programming, but also in quantum programming. So I could address them with qubit 0 through 3, but that's not readable. So let's give them names. And we'll initialize all of them to 0. Now, the quantum experience did that for us. Microsoft's Q# does not assume anything like that about the quantum computer it's running on. So it will force us to set these values to 0 first. And again, set them to 0 when we're finished, clean up after ourselves. This is because Q# is designed to be platform independent. Now, it's called Q# for a reason, because it is integrated into the .NET framework, which means here we have a C# program, and we're saying, okay, in this case, we want to run our code on a quantum simulator. Then we take the algorithm we just designed, plug it into that simulator, get a result, and then we can just handle it classically. So this allows us to very strictly differentiate between our quantum logic and our binary logic or classical logic. And this can be really, really nice as well. Microsoft, by the way, has also built a chemistry library that you can use to simulate, or to work with, I should say, quantum chemistry problems. Third tool for the day is Righetti Forest 2.0. Now, if you've seen this presentation anywhere before, this is the biggest update. Just a few days ago, Righetti, a quantum startup, because of course there are quantum startups, announced that they were deprecating and soon turning off their old API and replacing it with Forest 2.0. So Forest 2.0 is a quantum development SDK, and it, like Kisskit, is a Python library. It brings with it a specific quantum language, though, as does Kisskit, by the way. I just didn't get into that. In this case, called Quill. So here we have our algorithm defined in Quill, and we are defining at the top that we want to have 4 classical registers, 4 places in which to save our results. Then, you know the drill. We have the header mart, we have the C0, we have another C0, we have a third C0. So far, so boring. We've seen that multiple times now. And then we measure all of them, write them into our classical registers. Now, you can load this quill file into Python and run it as a program, or alternatively, you can write your program directly in Python using their library. So, I mean, here's the defining a register. Here are the operations, the actual algorithm. Here are the measurements. And you might notice that this is actually considerably shorter than what we had to do for Microsoft's development kit. And you can then run this on the quantum computers that Righetti is providing. In this case, I'm running it on a quantum computer that provides at least 4 qubits, which I defined right at the third line from the bottom, 4 qubits QVM. Now, why should you want to use Righetti if there are other bigger companies behind quantum computing? And one big reason you might want to use them is something they're starting, the Righetti Quantum Cloud Services. Now, they have an image on their website which explains nothing if you don't understand it anyway. But basically, this is going to be a cloud hosting service for hybrid quantum classical algorithms. So algorithms that use both classical logic and quantum logic written with Forest 2 can be run on their computers, can be hosted there, and you could use it like you would use, say, AWS Lambda, for example, but on a quantum computer. So this is going to be really, really cool. You don't have to host your own quantum computer. You can just use one of these quantum services. And right now, this is still in beta. You can register for the beta. I have done so. I haven't yet been allowed to join, sadly, but that should happen relatively soon. They're certainly hyping these new quantum services and building that up. So that should happen within the next, probably realistically speaking, couple of months. They're also working on building larger quantum computers at Righetti. Now, that's the tools. And one thing I've omitted so far is actually, why are we actually building quantum computers? I mentioned a few times that there are ways to simulate quantum computers. And I mean, if we can simulate them, isn't that easier than actually building them and cooling them down to temperatures colder than outer space and so on? And to answer that question, I'd like to go back to a previous slide. Remember this slide here? Now, in theory, when I press my clicker here, the dead cats should smoothly disappear and be smoothly replaced with gravestones. Let's see how that works. Yeah, that was not smooth. My computer is struggling with PowerPoint. This here is, as soon as the slide changes, there we go. This is Google's Bristlecone quantum computer, the largest quantum computer, as I said, outside of the D-Wave space that we as the public at least know about. Whether, say, the NSA has larger quantum computers, and I'm sure they're working on them, I don't know, but Google has announced this is one that they've got. This has 72 qubits, and that's the largest one, as I said, we know about. A few months ago, well, this was announced in March, and a few months later, the Alibaba Group, that Chinese internet conglomerate, came out with a paper saying, hey, we've done some simulations of quantum computers, and we simulated a bunch of different computers. Google's Bristlecone would be about here on that list, approximately in that area. And to do so, they used the Alibaba cloud services, and they needed 131,072 processors and a petabyte of RAM. Yeah, 131,072 processors. As far as I can tell, the processors they're using are 76 times 56.5 millimeters large. So if you take the long sides and multiply that by the number of processors they're using, you get to about 10 kilometers. Regular walking speed is 4 to 7 kilometers per hour, so averaging it out, all in all, you get to about 2 hours for just walking past all of those processors if they were lined up. That's a lot of processors. I mean, the memory, I said it was 1 petabyte of memory. That's 1,000 terabytes, which is 1 million gigabytes. It's 10 to the 15 bytes of RAM. Now, just to put that into perspective, a study I found says that a human body has roughly 3.72 times 10 to the 13 cells, which means to get to the number of cells that a petabyte has bytes, you don't need one person or even 2 people. You need 27 people. Divide them all up into their cells, count them, you're about at the number of bytes that you need in a petabyte. That's a lot of memory, and most of us don't have that lying around. So, quantum computers, we have resources. Let's say you're finally convinced you want to start looking into quantum computers. Where can you do that? Well, I already said we have the Quantum Experience. By the way, there's a link to the slide deck on the very last slides, so you can just download them and find these links on there. The Quantum Experience, you can register there for free. All of this is totally free. You can use Kisskit, Terra, and Aqua, which you can install locally using your regular Python tools if you're used to Python. The same goes for the Microsoft Quantum Development Kit, which is available for Microsoft Windows and Mac OS and Linux. That's no problem to get as well. And it works quite nicely. It's integrated into either Visual Studio if you're on Windows, or Visual Studio Code if you're on Linux or Mac. For Righetti, you can register on their website, though you have to scroll down a bit and find it down there. You have to give them your email address, which is a bit of a drag, but then they'll send you a link with all of the download information. And you can register for the beta of the quantum services. And if all of that is a bit too heavy for you, there's also a small game called Hello Quantum. This is written in Python. If you play it, it looks a bit like this. And I mean, there is a URL provided by the author of the game, which was just basically, well, it's far too long, so I shortened it via a tiny URL. You can get that there. You can download the source code if you like, look into it. This uses Kisskit and therefore the IBM infrastructure. And if this is all graphically too primitive for you, you can also get this as an app. So you can play quantum computing on your phone, and it's available for iOS and Android. Find it on the appropriate stores and start playing with that. If you need help with any of this, well, possibly except for the games, there's also Quantum Computing Stack Exchange. Literally Stack Overflow for quantum computing, made by the same guys. So you can register there and get help from people who know what they're doing. And that's that. Down here we have the link to get the slides. Go and play with quantum computers, and I think we have a bit of time for questions. Everyone totally overwhelmed and tired? Yes, there's a question back there. Okay, so the languages we saw look very similar to assembly, was the comment, and are there attempts to build higher level languages? I mentioned shortly that IBM has a language which allows you to describe just the quantum algorithm, and that's called QASM, short for quantum assembly. So you're not the only one to see the similarities there. And the answer is basically, yes, people are working on quantum languages. The big problem we're having so far, however, is that this field is so new, at least in the area of practical use, that we simply don't really know what we need out of a quantum programming language. People are certainly attempting that. I don't think any language has been particularly successful, at least in being widespread without the community, within the community. These languages will certainly come as soon as, well, basically we're ready. Also, of course, the actual quantum computers are still very, very basic, and they're not unified. The API for talking to IBM's quantum computers is totally different from the API for talking to Righetti's quantum computers. Microsoft hasn't even finished building a quantum computer. They're working on that. They already have the software, but not the physical device yet. So things will happen there, but we're not quite there yet. Any other questions? Okay, there's one thing I'd like to, that I have been asked in the past that I would like to talk about, and that's the term quantum supremacy, or as it's now mostly called, quantum advantage. You'll sometimes hear the terms, and basically they can be used interchangeably. Quantum advantage is now the preferred term by most people in the field, and this is basically the proof that a quantum computer can do something in a reasonable amount of time that a binary computer can't. This has long been worked on, and Righetti has offered a prize for the first people to be able to prove that. I think it was last week, IBM published a paper where, I haven't read the paper, but according to the abstract, they prove that in some chosen cases, they could mathematically prove Shor's algorithm to be faster for factorizing numbers than any viable solution on binary computers. Since I haven't yet read the paper, I can't really comment on that. I don't think that Righetti has announced that anyone, including IBM, has won the prize yet, so it's still, as far as I know, a bit open whether that quantum advantage has actually been reached. Also, keep in mind that having reached a quantum advantage does not necessarily mean that quantum computers are now useful for everything that one could use a quantum computer for. And also, you don't want to use a quantum computer for everything you would normally use a binary computer for, because I mean, a binary computer, if you ask it what's 2 plus 2, it'll tell you 4. If you ask a quantum computer, it'll say, I don't know, maybe 5 or 4 or 3. Here are the percentages for those answers to be correct. Yeah, I mean, that works, but I mean, why switch to quantum computers for something that already works really well with classical computers? Okay. Any other questions? Everyone just wants to go home, it seems. Thank you for listening, and yeah, no cats were harmed in the making of this presentation.